All right, so this is lecture 23, the last lecture in the section 4. So in this lecture, we will talk about ensemble method. And this is a very powerful family of machine learning models. And they mostly use a decision tree as the foundation to build ensembles. So that's why we introduced this after lecture 22, that is on decision trees. And in module 1, we will introduce you the basics of ensemble models. And then just to kind of recap where we are. So we have finished, after this lecture, we finish every part we want to cover about the supervised models. And let's get started.
So what is ensemble? So you can think about it, it's really a committee of prediction models and trying to do the job together. And then, yeah, so there's really this crowdsourcing and all this coming from a lot of those crowdsourcing ideas. So when we talk about ensemble, the general framework is normally like this. So you have base classifiers. You can just name or index them from F1x, F2x until we normally can write like FBX. And then the second stage is how do you aggregate, how do you blend all those different base classifiers together. So this is almost all the ensemble approach follow this framework. So there's this parameter very important is how many base classifiers, and there's another important or not. There's a lot of variation is how do you blend? How do you blend the different base classifiers together? So one important properties of ensemble models is so each of the base classifiers or base predictors, they should be diverse and very different from each other. So if they are too similar, and it really doesn't make a point at all to have multiple committees to vote together, right? Because they always have the similar votes. So this is one of the property make this type of ensemble model very appealing is, so what type of models has a lot of variations? And normally are those type of classifiers kind of vary a lot, which has high variance. High variance predictors are very good candidates for base classifiers, especially for if you use bagging type of blending. All right, so this is the roadmap we're going to cover about ensemble models. So there are roughly 3 kinds. Bagging-based, here the bag decision tree, which we covered, and random forest. And the second kind is boosting. There's famous ADA boost or gradient boost. So this is in the gradient boost. There are a few different toolbox, which is really famous in this category. Is they're all using the gradient boost idea for blending. So the bagging, the major benefits of bagging is to reduce variance. And when comparing boosting and bagging, so boosting has also the properties to reduce bias. So it's going to be clear when we touch the future slides, but just roughly have this bigger intuitions. Let's try to memorize now. It reduces bias, and also because the ensemble properties, they also reduce variance. And stacking is the third kind, which is just it's a more a meta learning more like a framework. So the stacking just it's more about how do you blend, and boosting and bagging are more specific ways for the blending, and stacking includes different kind of ways for the blending. All right, so what is bagging? So we already talked about bagging before. So the fundamental idea of bagging is use bootstraps of data samples in this case. So we try to just create a committee of decision trees. And then for each tree, we use a vote. Each tree casts a vote, and then together, when there's a test sample coming in, we're using majority voting from all the trees as the final decision. So this is a technique for reducing the variance for our estimated function. So basic idea we already covered, bootstrap and we're using bootstrap with replacement. So this is very important so for every bootstrap sample, which means we want to learn. So in the end, if you have your base classifier is decision tree, you already decided, and you want to learn F1, F2 to FB, B different classifiers, right? How do you create B different classifiers from one training data, from one training set? And there are really limited number of choices, right? You either change the training data, or you change the training samples, right? Because to make enough differences to train diverse, different kinds of different B-based classifiers, there has to be some differences among the samples, among how do you train it. And bagging is exactly using this. It changes the training set, but it doesn't change each specific samples. And how do you change the training set? And exactly is you sample, and then by using subsamples. But I want my different base classifiers to work on the same size of training sets. And that's just to make sure the variance, it's going to be clear later why do you want to have the same n, but just I want each of my new training set for each F1 onto FB have the same size. And how do you do it? The simplest way is to bootstrap with replacement. So question about this? So it just, you sample data, and you put it back, and you sample it again until you build a set. Maybe the first set is size n. And then you start to build the second set, again, from the original data, original training data, TR, and you create sample 1, subsample 1, bootstrap sample 1, bootstrap sample B. And each one of them has exact size as the size of the original training data, which we can use notation n. Right, so it can keep the sampling size the same as original for every repeated sampling. The sample data groups, so each of S1 onto SB are independent with each other because of the sampling process. All right, okay. So then it's create S1 onto SB, and on each that bootstrapped training set, you train a model. You just train a decision tree model, and you get B models. This is B different tree models. And then you put all these decisions together. So there are various ways to put the decisions together. The simplest is majority vote. You can also do summation. So uniform summation, which is, so each one of this is F1, F2, to FB. Then I can do my final F is 1 over B summation of I from 1 to B. So this is my ensemble version. So this is another way, right? So rather than doing majority, I'm just doing the mean score. I use that score as the final vector output projection. So that's the other way. All right, so so when you have new data, you just feed in the first F1, F2. Okay, so I already pretty clear. So if it's pretty 1, 1, 2, 1, and majority vote will give you 1. So this is majority voting, right? So the decision tree. So this is the decision tree. So if you have B different decision trees, so in the end, it's kind of smooth out the decision boundaries. So when we compare this model versus this model, so let's think about bias and variance trade-off. So we always previously talked about this, right? So what's the differences in terms of bias and variance trade-off when we compare the left to the right? Right, it has a much smoother boundary. So when you have a smoother boundary, so it means the variance is actually a lot smaller on the right? So the variance, so in the end, I want to compare the variance of this summation of Fi. So let's use, because it's easy to calculate the summation of, it's easy to have the analytic form of the summation function. So that's why I'm putting the summation function there. But you can also analyze, if you're using the max voting, you can analyze how the variance of this max voting grounded ensemble model. So so in fact, what we are comparing is variance of each Fi versus the variance of this. Let's compare specifically for this mean case. 1 over B summation Fi from 1 to B. Okay, so from the figure, intuitively, it seems variance got smaller. But how do you prove it? So this we talk about it. So actually, peculiarity of decision tree. The reason the decision tree is a high variance model make it a very good candidate as a base classifier to be used inside bagging. And so so we're going to talk about this later. All right, so let's come back to bias and variance trade-off. So to recap, so what is bias variance trade-off? So we always use this figure, right? So this is the generalization error. So using test samples to show it has this kind of bowl shape, and the complexity of a model shouldn't be too low. The complexity of your model shouldn't be too high. So when the model is really it has high bias, like SVM, that type of model compared to your data, it's very high bias, and you're going to have higher error, but the error is mostly because of the bias. So this figure, if you still remember, we use this figure to show, because of the high bias, so if you have smaller changes in your training data, your estimator, they don't distribute too wildly apart from the mean. So this means so this is when your model has low complexity, it has smaller variance. They're all very similar. When you have smaller shift in your training data, they all still distribute very closely. However, the mean of that estimation is very far from the truth. So this is the high bias. So the majority of the error is actually from here. it's the bias, right? So this is the bias case. And on the right, which when your model is super complex, when your model is super complex with smaller randomness in your training data, and we will just make the estimation distributed very wildly. And it can be here, can be there, can be in the middle, very close, but it just has a huge variation cloud. But its mean, the mean, so which means the average of all those models are closer to the truth. So if you only use one model, I mean maybe FI, it's maybe pretty far because the randomness, right? It's pretty far. The majority of that error was coming from not from the bias, not from the mean to the center, but from the variance, just because when there's smaller shift in your training data, smaller randomness in your training data, it might give you an estimator quite different, quite far from the mean. So this means high variance, right? The decision tree model, because you, in the end, you trying to explore all the possible combination among features. If you think about tree, what is the tree model? So we actually talk about tree models segment the space into rectangles. And assuming smaller rectangle, those local regions have the same prediction performance. Let's just see this. If there's a small randomness in my training data, I'm assuming this blue point is not just because of the sampling. This blue point is not sampled in the training data, then this whole small region will be gone, right? The blue region will be gone. And this actually means it's a very high variance model. But it's super flexible, right? If assuming you have a few blue points in here, I don't have blue color, but I'm trying to show you, it has the ability to just have a bounding box to show that should be the blue class, right? So the decision tree is extremely flexible model. Its decision is super nonlinear. It captures interaction among features, right? If you remember, it's a tree model. From the root to the leaf, it's a lot of decisions. In the end, it's an interaction from the root, from each level, each node, it's a feature. And then in the end, each path representing a very complicated interaction among many features. So it's an extremely nonlinear and flexible model if you have a very deep tree. So deep tree or wide deep trees, it's very, so if you have a full length of trees, it's a super flexible model. All right, so let's come back to this figure. So the tree, if you have the full tree or the majority, the big trees have very high variance. So then the issue here is to reduce the bias, right? Reduce the variance. Yeah. All right. So now let's see. So you have multiple classifiers, and each one of them corresponding to a estimation. Because think about the bootstrap samples. What we are doing in the bootstrap samples. If you remember, we bootstrap S1, S2 onto SB. In fact, we are creating randomness of my training data, right? And that create a lot of variations of the estimation of the different estimators, and by considering the randomness in my training data. Because this is a high variance model, it's very flexible, right? And then its mean is supposed to be closer to the truth. Okay, now let's just use the mean. And that's exactly the point of bootstrapping, and then together taking a decision from a committee of decisions. So we average all the F, and then their the average of all those F estimations, Fi, they are more closer. Actually, so this should be flipped. So this is the truth, and this is the estimator. So we average complex models to reduce variance, and then bootstrapping is to creating those randomness inside the your training data. So now let's see, how do you prove this? What is the variance of multiple random variables, right? That's the first equation we should look. So this is the general equation. When you have a random variable x and a random variable y, the variance of ax plus by, it follows this, it's an axiom. It's equivalent to a quadratic variance x plus b quadratic variance y, and then times 2ab covariance x and y. So in our case, who is x, who is y? So it's each estimator from different bootstrap samples, right? What I care is that variance of this bagging decision, which I just use a mean to represent it, variance of 1 over b summation of all the fi, you can actually derive this, and assuming this, it's actually not directly can be converted here. So in fact, I'm assuming all the F1 onto FB, their covariance equal to 0. Otherwise, there's no way I derive this. So when the covariance of Fi and Fj, all the possible pairwise covariance of each trees is 0. And I can derive, so because you have total of b, I from 1 to b, right? And I'm assuming each one of them has the same variance. So this actually can be approximated if the training data have the same size. So S1 size n, S2 size n onto SB size n. They are all the same size, and I actually can assume this almost guaranteed the variance of each Fi is the same. And then this equivalent to, because they're totally b, right? Variance, maybe let me write down here. So variance of F hat, which is the back version, they are 1 over b, summation of I from 1 to b, Fi hat, okay? And if 1, so that's just so 1 for all the I and j, covariance of Fi and Fj is 0, I can get the above is 1 over b quadratic summation of variance of each. And then, because of the sample size S1 onto SB, their sample size are all equals to each other, because, and then because we know S1 onto Sn, they're all, can that work? Okay. So S1 equals to S2 onto SB, they equivalent to each other. That's why I can roughly assume variance are approximately similar. The variance of Fi equals to variance of Fj. And because all those, and then this gives me what? The variance of F is 1 over B variance of each. which is this solution. So the variance of the bagged tree is 1 over b of each of the tree, assuming you're training the model the same way, and also each subset has the same size. And also, the different trees are not correlated with each other at all. They're totally, the covariance among each trees, all the tree to other trees are 0. And this is 1 over b variance f. So this sounds, why do I need to derive this, right? And it will be very clear later. So, okay, question about this. There's a lot of assumption here. I'm assuming all the trees are not correlated to each other. Their prediction are not correlated to each other. All right. Yeah, so okay, so now let me show you an example which shows the previous assumption doesn't hold. In fact, if you just do bootstrap and then learning decision tree on top, the learned trees are very correlated with each other. So let's use a extreme example, a very extreme simulated data to show you what is the behavior. So let's just assume a super small training data with only 30 examples, or maybe 300. So there are two classes, plus and minus, or maybe let's just do 0. So y belongs to 0 and 1. And you can just do normal simulation to sample 5 features and just normal distribute it. And you can also control the pairwise correlation among the features are super high, which in this case you can just control they are 0.95, which means this is almost equivalent to the homework 2 you did about ridge regression. And if you remember, so there's x1, all the other features are very, very correlated with x1. Actually, in the ridge regression or the other one? Yeah, in the ridge regression, maybe it's totally random, if I remember. There's another, yeah, so it's, in the end, you're simulating data to check the performance of your method, right? This is a very good sanity checker. So, okay, so now I'm generating x1, x2 onto x5. And they are almost the same feature. Each feature are very correlated with each other. And when x1 is bigger, and the other feature are also really, really large because the positive correlation, right? So x1, when x1 is large, x2, x3, x4, up to x5, they're all very large, which in the end means this data, it essentially has only one feature. But when you, in your observation matrix, these are 5 features. And then you just using a rule to generate y. So this is your generating training data to see if your decision tree can learn a good classifier, right? So it's a super easy rule. It just, if x is smaller than 0.5, x1 is smaller than 0.5 will be more likely to be class 0, y equal to 0. And then, and then if x1 larger than 0.5, and then, it's exactly that. When it's larger than 0.5, and it's mostly 1. When smaller than 0.5, it's mostly 0. So it's a super easy classification, actually. x1, and then there's a 0.5 there. So on the left is 0 class, and on the right is 1 class. And of course, this probability is to generate there's some kind of noisiness there, right? It's not fully deterministic. So you observe samples on the right, something like here, and sample here, but you still have a little bit of noise sample like class, and a little bit noise sample like this. So this is your observed sample. So the majority, if x 1 larger than 0.5, it's class 1. Majority when x1 smaller than 0.5, it's class 0. Okay, so why do I even care about this data? And then you use this data to learn a decision tree, to see if it can learn a perfect decision tree or a good decision tree or not, because this is the simplest ever data. And also it's the simplest ever decision rule, right? There's only one rule necessary. Let's see if your decision tree can learn it. Okay, so now you learn 500 trees. The problem, and in fact, what you're going to learn are many different kinds of trees. They look very, very different from each other because you random sample your training data, right? And because there's high correlation from X1 or X2 or X3 or X5, it's very difficult when you have just some randomness in your training data. It's very difficult for your classifier to pick which feature is the top feature, and then the next feature, and then the third feature. When should I stop? And what's the depth? When should I stop? When should I prune the tree? How should I prune the tree? So this creates a lot of different kinds of trees. They look quite different from each other. But because of this data, in fact, the trees are very, very similar predictions. So even though on the surface, the model looks very different from each other, but their decisions are almost similar. And whenever there's a fixed X of X1 onto X5, a certain test samples, the prediction of each F1, F2, so like F1X, F2X onto FBX, it's almost the same. So this actually tells you, even though the model looks very different from each other, but in fact, the decision is highly correlated with each other using the bagging trees, in the bagging strategies. So let's come back to see what, it's a little, I'm going to clean this up. What matters is what? What matters is the decision. It's a decision, right? I'm trying to reduce the variance of the decision in this case. Even though the model are quite diverse, but the decision are highly correlated, and there's no way a bagging strategy can work well on this data, on this type of so correlated data. So, and you can also tell, it really doesn't matter how many treat B when you increase the B. So roughly when B equals to 30, and the performance stops to improve at all. And in the end, the issue is the decision trees on the bootstrapped sample sets, it's highly correlated with each other. And they make very similar decisions. Okay, so this means what? When we do this variance of 1 over B, summation of Fi, and we actually cannot make that assumption. Covariance between Fi and Fj equals to 0. And that makes what? The whole variance of this summation, this ensemble, this bagging of trees, it's not necessarily got reduced if the covariance is too big compared to just each of individual trees. So this is the final conclusion, a summary conclusion I want to see about bagging decision trees. And then the whole reason is it's very correlated. It's only slightly increase the model complexities. And so because bagging tree are so correlated, then people come out with a strategy called random forest. The whole idea of a random forest to reduce the correlation among trees, which trying to reduce this item in this variance calculation in the end is now straightforward summation. also this correlation among models is truly important, and it's trying to reduce the correlation among different models.
Great. So this is the end of this module. See you in next module.